Okay, so here's how the week's gonna play out. Kind of jacked up. So today we're gonna finish up like applications and show you how all these equations like fit together historically and mathematically. Then review tomorrow. We don't have school Wednesday because of testing. And then the test is going to be on Thursday. Okay? So just kind of the big picture. All right. So here's big ideas that you absolutely have to understand. Okay? And then we'll see how those actually in a weird way tie back in with Kepler's laws. So here's, if you look at certain equations, you're like, okay, we're going to lose all information of science. But we get this, but we have to start over. What are some equations that we would like to have to start over? So in other words, we're going to lose it all, but there's some that we get to like keep. Without doubt, this would be one of them, okay? Because this explains basically how the universe works to a large degree. So you have to understand what Newton did and what Newton didn't do. Newton basically said, look, I'm a big idea kind of guy. All I know is that the gravitational force between two objects is directly proportional to the two masses and inversely proportional to the distance between them. And then he said there's just some constant of proportionality. Okay? He goes, I don't know what it is. I don't care what it is. I'm going to leave that up to someone else. So Henry Cavendish, he actually built a separate room onto his house to develop this value. Because he didn't want to be in the room because he was afraid his equipment was so sensitive. He was afraid that if he was in the room, his mass would interfere with the results. And it was that sensitive. And if you take AP Physics 2, you're going to do a lab, and you can witness this. In AP Physics 2, we do a lab where we charge the balloons and we try and figure out the charge on the balloons. And because you're part of the system, you interfere with the balloons, and it's tough to get away from that. So that's how sensitive his equipment was. So Henry Cavendish comes up. He comes up with big G. Now, here's the next big idea. Like we talked about this. If we wanted to calculate how much Caitlin weighs, we could take the mass of Caitlin times G, and that would equal big G times the mass of Caitlin times the mass of the Earth over R squared. Okay, and again, nothing against Caitlin. Okay, she's a wonderful person. It would happen to any of you. Elliot, Dylan, Vanessa, it doesn't make any difference. Everybody's going to drop out of the equation. So what you're left with is this idea. The little g equals big G, mass of the Earth over R squared. Understand what that little g gets you. That little g gets you the gravitational acceleration when you drop something. So if you've looked at those problems that you have to work. So when you get to question number 2, it's like, oh, okay. What's the distance that you have to be where a 1 kilogram mass weighs 3 newtons? Okay? So there's a couple of ways that you could approach this. One option is that you go, okay, right. On Earth right now, right here in this room, what would a 1 kilogram mass weigh?
9.8 meters.
How'd you get that number?
Times,
9.8 meters
yeah.
per second.
You took 1 kilogram times 9.8 meters per second squared, and you got 9.8 newtons. Cool. Okay? That's one way you can get this number. The other way you could do this is like, oh, Burkamp, I want to go old school. The other thing that you could do is you could take big G times 1 kilogram times the mass of the Earth divided by the radius of the Earth squared. Okay, it's a lot of math, but if you did this, you would still get 9.8 newtons. Okay, and this is what's important. If you had a 2 kilogram mass, you would put 2 kilograms in there, and obviously the amount of force would double because of the fact that you're doubling the amount of mass that's being attracted to the Earth. Okay. So you could do this to calculate the weight of anything. Notice I did not say mass. I said weight of anything. So here's the other way that you could do this. Knowing this, that you would get 9.8 newtons. I don't recommend it, but this is important that you understand the conceptual side of this. So you could come over here and go, okay, hey, that's 3 newtons. That's what I want the force to equal. Okay? That's what you want it to equal. It's 3 newtons, not 9.8. You want it to equal 3 newtons. So then you've got big G. It's a mass of 1 kilogram. You got the mass of the Earth. And then you've got distance squared. Solve for distance squared. Multiply by d, divide by 3 newtons, take the square root of that. Okay? It's a lot of work, but it works. Okay? But this is one of the reason I put that in there is so that you understand fundamentally what creates weight is the gravitational attraction between 2 bodies. Okay? That's what creates weight. Now, the other thing that you could do is if you realize, well, if it's going to weigh 3 newtons, that would mean that I'm taking 1 kilogram times 3 meters per second squared. Okay? That's what you would do. Okay? If G on Earth was only 3 meters per second squared, if I said, hey, what does a 1 kilogram mass weigh? You would go, oh, Mr. Burkamp, that's easy. 3 newtons, 1 times 3 meters per second squared instead of 9.8, we're going to pick 3. Okay? Sports would be more entertaining. Okay? Because you can throw the ball a lot farther. Okay? It'd be easier to dunk. But, you know, there's not as much gravity. So, knowing that this has to be 3 meters per second squared, then you could go to little g equals big G, mass of the Earth over r squared. Now you want this little g to be 3 meters per second squared. You know big G, you know the mass of the Earth, solve for the radius. Okay? So that answer to number 2 should be something times 10 to the 7th. Okay? Obviously, you have to be a long way from the center of the Earth for that to happen. Okay? Cool with that. Now, the other thing, if you go back up to where we started, since centripetal force equals your gravitational force, and again, on the front of the test, I'm going to tell you straight up, here's the equations I'm going to give you. Little v, one for velocity, this Swiss Army knife equation that allows you to solve for mass, period, or radius. This one that allows you to come up with a value for your gravitational acceleration. So these 3 right here. This one, this one, this one. Front of the test. Don't memorize them, don't store them in your calculator. I will give them to you. You just have to know how to use them. Okay? Good with that. Now, the other idea is that because centripetal force equals gravitational force, if you're in orbit, and I have to stress this, very, very near to the surface of any planet, okay? This doesn't work if you're further out. But if you're in near Earth orbit or near lunar orbit, whatever, near Saturn orbit, whatever, it doesn't make any difference. You can set the centripetal force equal to your gravitational force, okay? Because that's the basic idea. Oh, well, my centripetal force is mass times my centripetal acceleration. This is going to be mg. This would be the mass of Caitlin, mass of Caitlin. Again, Caitlin cancels out. Okay? So your centripetal force, your centripetal acceleration always equals your gravitational acceleration. Now, if this is the important part of this, if you're close to the surface, and that's a huge caveat, if you're close to the surface, like if I take the squirrel and I throw it, oh yeah, I'm close to the surface. If I do that, and centripetal acceleration equals g, then you know, oh, well, centripetal acceleration is v squared over r, and that equals g. So then I can multiply both sides by r and take the square root of that, and I get v equals the square root of g. Now, where have you seen that equation before?
With the finding the minimum speed to.
The minimum velocity to complete the loop, okay?
Oh.
Keep in mind, now, I'm gonna tell you straight up, there are two parts to this test. There's the centripetal acceleration part, and there's the gravity part of it, okay? They're both interlooped into this. Do not wait until Wednesday night or Thursday morning, oh, I guess I better go back and look at that. You better start going back and looking at and refreshing yourself on all of that centripetal motion stuff. What happens at the top? What happens at the bottom? How does friction be a part of the story? Okay? So, the reason that this works is that, like, if you're in near-Earth orbit, oh, that's just 9.8 meters per second squared times whatever the radius is from the center of the Earth, okay? Basically, it's a really, really big circle, okay? So if you're talking about the moon, you would put in the radius of the moon. Now, the only reason that that works in near Earth is because once you get beyond, if you're very far away from the surface of the Earth, G is no longer 9.8 meters per second squared. It can still work, okay? You just have to use what that value is at that point, okay? So it might be 9.3, it might be whatever that is. So if you're told that something's like in a very near Earth orbit or near lunar orbit, there's some questions like that in the book, you can just use V equals the square root of g, okay? But it's limited to something that's close to the surface, all right? And you would be told that, hey, something's orbiting close to the surface. Okay, so if you look at this historically where we're at, Tycho Brahe collects all the data. He passes away, Kepler steals the data. 15 volumes worth, according to our historian, Dylan Anderson. He takes the data, goes back, comes up with his 3 laws of planetary motion. These are not suggestions, these are laws, okay? I'm not going to expect you to know specifically like, hey, what's the first law? But I am going to expect you to know the big idea. So the first law is the law of ellipses, okay? So that means here's this orbit. The sun is at one foci, the other one is some point out in space, okay? First law. Second one is the law of equal areas in equal times. So that means if you draw a vector from here to here, and you draw another vector out there to the edge of that orbit, those areas are the same. The only thing I'm going to expect you to know from that is that if you decrease the radius, you increase the velocity. Or if you increase the radius, you decrease the velocity, okay? Kepler never tried to explain why this works, which we'll get to in just a second. He basically says, hey, here's the deal. Why it works, I don't know, but this is what I observed. Third law. This is the rate. This is what he was actually after. Okay? And this is a ratio of 2 orbits that have to center on the same object. Like we can compare the Earth and Mars because we both orbit the sun. We could not compare the orbital period of our moon to a moon of Jupiter because they don't orbit the same center. This is the only time I will ever say this to you. It doesn't make any difference what units those are in. They just have to be the same. Okay? As long as you're working with a pure version of Kepler's third law, doesn't make any difference because it's just a ratio. Period could be in days, hours, seconds, doesn't matter. Radius could be in astronomical units, kilometers, meters, doesn't matter because it's a ratio. Okay? Now, if you're using anything that involves big G or any of the classical computations, you have to be in the MKS system. You have to be in meters, you have to be in kilograms, you have to be in seconds. Otherwise, all the units just fail, okay? So, Kepler publishes this early 1600s. Newton comes along in the late 1600s. He says, hey, let's try and figure this out, because nobody really understood why it worked. So, let's start with the idea that centripetal force equaling mv squared over r. And then, so as this, say Mars, goes around the sun, is that m the mass of Mars or the mass of the sun? Mars, because that's what's moving in the circle, right? So that'd be the mass of Mars. Now, interesting thing happens. As it gets closer, what happens to the velocity? It goes up, and it gets squared, okay? What happens to the radius? It becomes smaller. So what happens to the amount of centripetal force that Mars needs to slingshot around the sun? Does it get bigger, smaller, or stay the same? It gets bigger. Same mass, you're moving faster, and you're dividing by a smaller radius.
So bigger.
So yeah, the centripetal force gets bigger, okay? It's like in your house, you have a banister and you run by it and you grab a hold of it and you like slingshot yourself around. That's basically what Mars does around the sun. Cool. So when you're closer, you need more centripetal force. Great. Now, what's the only possible source of that centripetal force?
Gravity.
Gravity. There's no strings, there's no friction, okay? It's just gravity. Ah, look. So that gravitational force is going to be mg, big G, mass of Mars, mass of the sun, over distance squared. Cool. What happens to the top part of that equation through its orbit? Do not make this difficult. Does the top part of that equation, big G, mass of Mars, mass of the sun, change as it goes through its orbit? No, there's no change. Everything's based upon mass and big G. So the top part of that equation doesn't change. It's a constant value. But when you get closer, what happens to the distance?
Decreases.
Well, it decreases. So you're dividing by a smaller number. So when you divide by a smaller value of distance, what's going to happen to the gravitational force between Mars and the sun?
It's bigger.
Oh, it's going to get bigger. How cool is that? This is why it works. As Mars approaches its orbit, you need more centripetal force because you're moving faster with a smaller radius. Conveniently, gravity sits there and goes, I got you. Okay? I got you. So gravity is going to get stronger to create that greater centripetal force. Now, you go out here. What's going to happen to the amount of centripetal force that you need?
Decrease.
Because you're going slower and you're dividing by a bigger radius. Centripetal force goes down. Gravity says, I'll chill out. Okay? Because then gravity says, I'm going to divide by a bigger value of distance. Ah, cool. Gravity's not providing as much force. They go hand in hand. And it has to. You couldn't need more centripetal force if gravity was getting weaker when it was closer. It's just not possible. That'd be like you trying to take, hey, it's an ice storm, but I want to take a really tight turn through my neighborhood at 50 miles an hour. That's a recipe for disaster, okay? Because friction goes, no, not going to happen. And so that's what gravity does. Gravity goes, I'm stronger. You need more centripetal force? I can do that. Now, what if, it doesn't, but what if all the orbits were perfectly circular? Would the amount of centripetal force that you need change? No, but guess what else wouldn't change?
The radius.
The radius, so therefore, what else wouldn't change? Rhymes with gravity.
Gravity.
Gravity. So the gravitational force would stay the same. Cool. Okay. Now, according to legend, okay, Newton publishes his works, and he's talking with a colleague. His colleague says, we got Kepler's third laws, but we don't know why they work. Now, according to the story, Newton shuffles through some papers or opens up a drawer. He says, oh, okay, I got this all worked out. This is why it works. And the guy looks at the work and goes, why didn't you publish this? And Newton goes, oh, it's really not that big a deal. So let me explain what was on Newton's paper. So let's say that we have some star alpha. Okay, it doesn't make any difference, it's some star. And we have two planets, number 1 and number 2, that are orbiting this star. Okay? That's what you've got. So when you do this, this is why it has to orbit the same center. So if you look at that equation, that big one, that Swiss Army knife equation, where you've got 4 pi squared r cubed equals big GM. So you got 4 pi squared r cubed equals big G mass of alpha times t squared. Okay? So this, and you're going to need to be able to do this stuff on some of the, especially the problems out of the book. Okay? So we're going to set this up as a ratio. Okay? So this is going to be the radius of 1, mass of alpha, period of 1 squared. Now, for the second planet, that's going to be 4 pi squared r2 cubed. It's going to equal big G mass of alpha over T1 squared. Okay? So, because of the fact that we want this as a ratio, I'm going to take this, because it's a ratio, like 4 to 5 or 3 to 8, whatever it is. Okay? So I'm going to take what's happening with period 1, and then I'm going to divide that by what's happening in the second one.
Well, I think I had that off of Acers. Continue.
Thanks. Okay, so if you set it up as a ratio, and here's the cool thing, what happens to the 4 pi squared?
Cancels out.
Cancels out. What happens to big G? Cancels out.
And then you get the,
What happens to the mass of alpha? Cancels out.
Oh, we already got this.
yeah.
Oh, what are you left with?
Oh, no, we got
Kepler's third law. Okay? So, according to the legend, Newton goes, look, all you have to do is just set it up as a ratio. These are going to cancel out, and then you're left with Kepler's third law that says R1 cubed over R2 cubed equals T1 squared over T2 squared.
Huh.
There you go. This is why it works. Now, this is why, mathematically, you have to orbit the same center. Because if they're not orbiting the same center, then the masses don't cancel out. Okay? So mathematically, this is why they have to orbit the same center. All right. So fast forward 300 some odd years. These equations work. Newton's laws of universal gravitation worked. Kepler's law worked. We were very, very good at predicting the motions of the planets. If you tell me where any of the planets are, I can tell you where they're going to be in 10 years. I can tell you where they were 40 years ago because they were so predictive in nature. But nobody really kind of understood why it worked. They had the math. The math worked beautifully. But they didn't understand why. So Einstein comes along, early 1900s. Develops two theories, theory of special relativity and theory of general relativity. So what he did is he viewed space and time as a fabric. Okay, so let's see what that looks like. So stop you on the camera. bring that back.
I was gonna ask a question on this too.
Huh?
I was gonna ask a question on this.
We'll get back. There'll be more.
Like on my trip,